Good afternoon. I am Shailendra Singh Ojha, Assistant Professor in Department of Electronics and Communication Engineering. Today I am going to discuss high frequency model of BJT. As we all are aware about the BJT, that BJT is a bipolar junction transistor, and this device is used as a amplifier as well as switch. If we are going to use this device as a switch, that means it can work as a either on or off, but its wide uses are as a amplifier, and we all know that amplifier is a device which is used to amplify the signal, which is used to increase the signal strength of the signal, and this device behaves differently for different frequency ranges. Due to this, we need to understand that how does this device will behave at low frequency signals, at low frequencies and at high frequencies. That means how does it will behave for the signal of low frequency and for the signal of high frequency. Obviously, it will different somewhat differently, that we are going to discuss today. As we can see, this is the high frequency model of transistor. In the case of low frequency transistor model, these capacitors are ineffective. That means their effect is negligible at very low frequencies. So at low frequencies, this model will be simply consist of R pi, GM V pi and R naught. But at high frequency, this is Rx, C mu and C pi. These are the three more parameters that will come into the existence, and this is the high frequency R pi model, and this is the high frequency T model. If you will see here, then you will come to know that there are two capacitances. One was C pi and another was C mu, and from that C pi is the emitter base capacitance, which consists of CDE and CJE. That means there is another capacitance which is base collector capacitance, and you know that C pi is in the ranges of picofarad to few 10 of picofarad, and C mu ranges in the fraction of picofarads to few picofarads, and Rx is in the range of few ohms, and its value depends on the current level in the somewhat complicated manner. And R pi, we all know that what is R pi. So if you will talk about these capacitances, then a small singlet diffusion capacitance is the CDE, and base emitter junction capacitance is the CJE, and collector base junction capacitance can be easily found out with the help of cu mu is equal to C mu naught upon 1 plus VCB upon VOC, where C mu naught is the value of C mu at 0 voltage, VCB is the magnitude of collector base junction reverse bias voltage, and VOC is the collector base junction built-in voltage, which is around 0.7 volt, and M is its grading coefficient, which is typically from 0.2 to 0.5. Actually, next we can talk about another parameter, which is the unity gain frequency. And as its name suggests, that unity gain frequency is the frequency at which gain is equal to 1. So let us see and let us drive an expression for the unity gain frequency. We have connected the voltage source VB, and we are considering that the current IB is flowing due to this, and the voltage drop across V pi is the voltage drop across R pi is the V pi, and we are considering that the current which is flowing here is SC mu V pi, because the voltage here and here is V pi, and current flowing through this will be simply SC mu, and we are considering that this current I naught is flowing here, which will be equal to the Gm V pi current which is flowing in this branch minus the current which is flowing here. So it will be equal to Gm minus Sc mu into V pi. Now the short circuit collector current, that is IC, and IC will be equal to this Gm minus Sc mu. Now let us find out the relationship between V pi and IB, and it can be established by multiplying IB by the impedance seen between the B dash and E. If you will see here, the impedance between B dash and E is this and this. That means it consists of R pi, C pi and C mu, and these three are in parallel. So the equivalent impedance of these three, and it should be multiplied by IB, and if you will do multiplication of these two, then we can easily obtain V pi. Now the parallel combination of one R pi, C pi and C mu will be equal to 1 upon R pi plus Sc mu plus Sc pi, and IB will be in numerator, so you will get IB upon 1 upon R pi plus Sc mu plus Sc pi. And we all know that HFE is nothing but IC upon IB, and IC we have already found out, and IB can be found out from this. That means IB will be equal to V pi into 1 upon R pi plus Sc mu plus Sc pi. So if you will solve it, then you can easily find out. Actually, from here you can find out IB is equal to V pi into 1 upon R pi plus this S C mu plus C pi. In this way you can find out this. So IC upon IB is Gm minus Sc mu into V pi, and it will also be multiplied by V pi, and V pi will be cancelled out. So you will simply get HFE, that means current gain, which is equal to IC upon IB will be equal to Gm minus Sc mu upon 1 upon R pi plus S C pi plus C mu. Now as you know that at the frequencies for which this model is valid, that means for the high frequencies, omega mu is much less than Gm. That means we can approximate that Sc mu will be very small. So you can easily write HFE is equal to this Gm, and if you will take its LCM, then you will get Gm R pi upon this S C pi plus C mu and this R pi. So this is how you can find out HFE. Now actually we are going to find out unity gain frequency. So in this case you can easily write that this is Gm R pi. We already know that Gm R pi is equal to beta, and Gm R pi more correctly we can write that it is equal to beta naught, and beta naught is the low frequency value of beta. So HFE has a single pole or single time constant response with 3D frequency. So at omega is equal to omega beta, we can write omega beta is equal to 1 upon C pi plus C mu, and that means it follows that the frequency at which HFE drops to unity, which is called the unity gain bandwidth omega t, and it will be given by omega t is equal to beta naught into omega beta. Now what is omega t? Omega t is the unity gain frequency, which will be equal to Gm upon C pi plus C mu, and if you will put omega t is equal to 2 pi ft, so you can simply write ft is equal to Gm upon 2 pi C pi plus C mu. And if you will see here, as you all are familiar with this GM, this is high frequency model, R pi high frequency model, and this is the T model for the high frequencies. And we all already know this from low frequency model, that GM is equal to IC upon VT, where GM is the transconductance, IC is the DC bias collector current, VT is the volt equivalent of temperature, or we can say thermal voltage, which is nearly equal to 26 millivolt at room temperature. And earlier we have already found out this, C pi plus C mu is equal to Gm upon 2 pi ft from this, and we already know this. And R naught is equal to VA upon IC, where VA is the early voltage, and IC, you know, IC is the DC bias collector current. So R pi can also be written as beta upon GM, and in this way you can proceed to solve these type of circuits, or you can derive an expression for the unity and frequency. Next is the common emitter amplifier. If you will consider common emitter amplifier, and its equivalent circuit can be drawn like this. This is actually the high frequency model, and RC and RL are the externally connected resistors, and RB and R signals are also the externally connected resistors along with the V signal. If you would like to see, then the actual circuit will be somewhat like this. RL, V naught, and this is something like this. RB, coupling capacitor, and this V signal, and here will be the resistor RB, it will be the resistor R signal, sorry, and this is the V signal. Or even it can be like this also, emitter bypass capacitor. This is the RC. So its equivalent circuit can be redrawn like this, or the high frequency equivalent model of common emitter amplifier will be like this. Now let us analyze this circuit. If you will draw its reduced form, or for the better analysis, we can redraw this circuit like this. This is the R dash signal, and this is the V dash signal. It will compensate for all. That means it will compensate for this voltage and these resistances, along with R signal, RB, R pi, Rx, and towards output side, this RL dash will consist of the equivalent combination of this RC and RL as well as R naught. So it is very easy to understand. The parallel combination of these three is represented by RL dash, and this R dash signal is equal to R pi with the parallel combination of R pi plus RB in parallel with R signal, or you can simply consider this, that RB in parallel with R signal. Okay, then RB, R signal, then Rx, and these two are in parallel. Then Rx and their combination of these three will be in parallel with R pi. So you can easily write R dash signal is equal to R pi in parallel with Rx plus RB in parallel with R signal. And similarly, V dash signal is equal to V signal multiplied by RB upon R signal plus RB multiplied by this resistor R pi upon R pi plus RB Rx plus R signal in parallel with RB. So, in this way you can draw its equivalent circuit like this. Now, let us find out the midband gain for this circuit, and the midband gain for this circuit is equal to or actually I can say that at midband C pi and C mu will be 0. So, you can easily write AM is equal to V naught upon V signal, which will be equal to minus RB upon RB plus R signal multiplied by R pi upon R pi plus Rx plus R signal in parallel with RB multiplied by GM RL dash. And you know it very well that RL dash is equal to R naught in parallel with RC in parallel with RL. So, you can write the final result as like this for the high frequency model. V naught upon V signal is equal to AM upon 1 plus S upon omega H, which is the response of the low pass filter. Soon we will discuss that how does this circuit will behave as a low pass filter. So, from this you can write FH is equal to omega H upon 2 pi, which is equal to 1 upon 2 pi C in into R dash signal. Actually, this is obtained from the response of low pass filter, for which cutoff frequency FH is equal to 1 upon 2 pi RC. So, C in and R dash signal. So, with the help of these expressions, you can find out C in is equal to C pi plus C mu into 1 plus GM RL dash, and R dash signal is equal to R pi in parallel with Rx plus RB in parallel with R dash signal. So, if you will see here, this is the response of the BJT at high frequency. That means how does BJT will behave at high frequency. This is the response at the mid frequency. That means gain will be almost constant. After that, it will keep on decreasing. And if this is the maximum gain, that at the minus 3 dB, the gain obtained is the minus 3 dB gain, and this frequency is known as 3 dB cutoff frequency. And if I will ask you to draw low frequency response, then low frequency response will be like this. That means initially the gain will be low, then it will keep on increasing, then it will become constant, and finally it will keep on decreasing at high frequency. So, this is how the gain will vary with respect to frequency for the amplifier. And there is one more thing that we can discuss is if you will cascade more amplifier, then what will happen to gain and frequency. See, actually gain and bandwidth product is constant. So, if you will cascade various amplifiers, then obviously their gain will increase, but bandwidth will decrease. That means if this is the response of single stage amplifier, then for second stage amplifier, two stage amplifier, the gain variation will be like this. Bandwidth has been increased, but gain is decreasing. If we will connect more amplifiers, then bandwidth will decrease, however gain may increase. So, this is how the gain and bandwidth varies for the amplifiers if we will connected them together, and this is how we can find out unity gain frequency and high cutoff frequency